All right, welcome back, everybody. Uh, this is going to be lecture 10 of PSTAT 100. Um, in lecture 9, we introduced ourselves to simple linear regression. Theoretically, we defined the model, um, and we performed ordinary least squares to estimate the parameters and derive the closed form expressions for the parameter estimates in the simple case with one predictor um, for the one response. Um, Now that we've kind of covered the theoretical basics, kind of the fundamentals, we'll move on to looking at how we actually perform linear regression in Python with a couple of different data sets going through the penguins data set for our example, with a focus on how we apply um, the formulas that we derived last week quickly and efficiently using packages. There's a load of different packages we can use. I will probably flip between them during this course, depending on what we're doing. I know scikit-learn has a linear model package function, which I'll probably use at some point. But for today's class, we'll be looking at, I believe, the one from statsmodels. But there's by no means just the one way of doing this on Python. So for a quick overview, the aims are to load a real data set. So we're going to be looking at the Palmer's Penguins data set. We've already performed quite a lot of exploratory data analysis on this data set. It's just very easy to understand and to digest, whilst we're keeping things nice and simple. We're going to have a quick recap of the exploratory analysis, specifically what we are aiming to look at when we are trying to apply linear regression. Before we then proceed to fit a simple linear regression model using statsmodels, we'll carefully break down all of the different sections in the regression summary output, and we'll interpret how we read them. And then we'll talk about how we produce visualizations alongside confidence and prediction bands. This is where the code can get a little bit denser, but typically it's all just pulling information available from the fitted model that we've saved as some object, and it's just syntax, knowing how to pull it and then how to transfer it into different figures. Lots of options for using AI agents to speed up this process, and more the focus on what visualizations we're interested in, what they're telling us. But the syntax is also important to know. It's kind of using matplotlib most of the time because it's very custom to what we want, rather than using something like Seaborn, which only produces these plots that are used frequently. We'll then conclude the lecture by looking at the diagnostics of the model. So a big question after we fitted models is how well does that model fit the data? Not just how good is the fit, but is there any evidence of problems, or is there any evidence that our initial assumptions before fitting the model were flawed? To check those assumptions and to check the fit, we carry out residual diagnostics. So we'll define what residuals are. We'll check them against the Gauss-Markov assumptions, which are the underlying assumptions for this model. And then we'll kind of go through a very, very common or a very well-known example of why diagnostics matter through this Anscombe's quartet, which is a collection of 4 different data sets that all have the same summary statistics, but don't have the same appearance once we plot them. So sorry, my face is in the way again, so I'll make myself a bit smaller in the bottom corner. But we'll be using the statsmodels .formula.api package. So the API section of the formula section of the statsmodels, we'll load it as SMF, and then also we'll just load the general statsmodel API as SM. But we'll only be calling one function from this package, so it's nothing too comprehensive. As always, we set our figure styles, but to crack on, we start by quickly summarizing the data set again. So we've seen Palmer penguins several times. It is this clean and well-studied data set that's recorded from 3 penguin species on islands near Palmer Station in Antarctica. So we've already had a look at some of the different physical measurements it includes, but one combination is flipper length and body mass. So we can load the data as always. In this case, I've used or sorry, I should say my AI agent seems to have changed it to the Seaborn loading. version, but this is just doing exactly the same thing as. Oh no, it hasn't. It wasn't the AI agent. It's because Penguins is being loaded from the Seaborn package, so we need to use this package from this package load dataset from Seaborn. My apologies. Um, just a quick examination. We still have some missing values. We won't be worrying too much about being very rigorous with the dataset. We'll just drop the missing values when we perform the regression. We start by posing a modeling question. So the idea is that can we predict a penguin's body mass from its flipper length? Specifically, can we model penguin's body mass as a linear combination or some kind of linear model where the input is flipper length? Keeping things simple, this is as simple as it gets. We have one predictor, one response, which is why we're using simple linear regression. Predictor is flipper length, the response is body mass. We remove all the missing values using drop NA. So I've just dropped all of the missing values from the data set. That have missing values in these columns of the data set, and then just print the response to penguins.info. This is just kind of good practice in terms of as much as we've seen it before, just kind of getting the algorithmic approach of just producing these same results every single time. We can see that after we've removed the data, we have 7 columns with 342 entries that don't have any missing values in those 2 columns. If we want to, since we are only considering these 2 variables, I produce a quick summary statistics plot. For flipper length and body mass exclusively. So I isolate those 2 columns, use the describe function, which produces this nice selection of summary statistics, and then just use round 2 to stop having to not have unnecessary detail in the decimals. Not really particularly informative. We've already performed our EDA, and so I'm not going to delve into examining the distributions of these things. More than the next plot, which is just producing this grouped histogram. This is more to highlight something that we'll discuss later on, but this idea that there is some underlying grouping happening in this data set. It's kind of the key point of this data set is that we have different distributions and different relationships depending on the penguin species. And so by grouping the histograms by penguin species, we can see this differentiation of the different species and the distributions of the different species. And this is something to bear in mind once we fit our linear regression, because one of the checks that we perform on the residuals is to look for banding and essentially looking for some evidence that there are clusters of residuals behaving in different ways, which indicates that there is some underlying confounding variable. In this case, it's this categorical species variable. So just something to bear in mind. I think I make a note about that in a second. But in terms of exploratory analysis tailored specifically towards regression, the most important plot is obviously a scatter plot. This is so that we can visually inspect for this the properties of data or the underlying linear relationship that we discussed last lecture, these Gauss-Markov assumptions. We're looking to see that the noise term, or sorry, that the first of all, that we have this lack of heteroskedasticity. We're looking for evidence of a linear relationship. We're looking to see if that linear relationship is straight or curved. In case it's a polynomial relationship, in which case this might not be a very good decision and to fit the model, to fit a linear regression model. The scatter plot, to quickly summarize everything I've just said, we're looking at linearity. Does the relationship look approximately straight? If we have strong curves, a linear model might not be appropriate. Do we have constant spread, or do we have some kind of bugling or fan shapes appearing, whether we have some kind of type variance, and then as we move along the predictor, the variance seems to get larger and larger. That would be evidence of this heteroskedasticity, which is a violation of one of the assumption number 3. And so in that case, we would consider not using the linear regression as well. As always, we look for outliers and the unusual observations. So this can be kind of very broadly stated as any points that seem to be suspiciously far away from the main cloud. These can have a very strong influence on the fitted line. They can have very high leverage and pull our best line away from the kind of general trend of the data. And so that's just something to look out for. And if once you're performing more sophisticated regression, you typically perform kind of an analysis, or you try and determine whether or not you should include those outliers or not, or whether they are distorting your final results sufficiently. And then, as I mentioned before, we're also looking for clusters and subgroups. So any sort of grouping or clustering that seems to come through visually may suggest some kind of underlying variable. In this case, it's probably what we're going to see, but let's produce a scatter plot. So producing the scatter plot using Seaborn, kind of copied and pasted this, I think, directly from the EDA slides from a few weeks ago. We can see some evidence of clustering. We're going to forget about it for now, essentially just assuming that we don't know what the species are. But we can see that we have a cluster of one species higher up, and then the kind of a cluster with the other two species lower down for different flipper lengths. That clustering aside, which would potentially be something to consider when deciding to do simple linear regression, we can definitely see this clear linear trend that doesn't seem to be curving, and there doesn't seem to be much bugling or fanning. The variance across the cloud seems pretty constant, potentially wider at the bottom and tighter at the top, but in general it seems quite reasonable. So other than this clustering, let me unhighlight that. Other than that clustering, this seems quite reasonable for a linear regression model, and so we can proceed to our fitting. Just before proceeding to our fitting, I should say, I'm getting my own slides out of order. We can try and quantify this linear association, so we can just double check mathematically if there's this the size of this linear association, and we do that using the Pearson's correlation coefficient. So we've done this a few times, and I think we'll do it on Monday in the lab on EDA of multivariate exploratory data analysis. But we can basically use this correlation function on a data set, and it will return the correlation matrix, whereby we can look at the row compared to the column observation to see the correlation between those two variables. We can see here that body mass and flipper length has a very, very strong positive correlation of 0.87, which indicates this very strong positive linear association between flipper length and body mass. Extracting this value specifically, we just pull the correlation for this corresponding value. So you can see here we've just defined our correlation coefficient as R by pulling out this 0.872, 0.8712 from the matrix. And we're just printing R and R squared. R squared is, in the case of simple linear regression, just equal in terms of capital R squared, which is what we look at in the output. We'll talk about that in a second, is essentially the same, or is exactly the same in simple linear regression as the Pearson's correlation coefficient squared, but that doesn't hold in general for multivariate regression. And we'll kind of cover that in a second. So the way to interpret this result, the R squared here, because this is, like I said, the same as capital R squared, which we'll get from our linear regression. Flipper length explains about 76% of the variance in body mass, which is a strong relationship, but is not perfect. So there's still room for improvement, or still potentially better fits out there, but this is still very good, and we can proceed to fitting the model. So as I mentioned, we're using stats models. There are two different interfaces that we can use for stat models to fit a simple linear regression model. I've just copied again my import from the front page to kind of see where this SMF prefix is coming from. So we're pulling ordinary least squared from the stats model formula API, and the syntax in the formula interface, which is what we will prefer in this class, to keep the readability very good. But we typically may need to rely on the array interface when we look at multiple linear regression, but not to get ahead of ourselves. The formula interface is very similar to modeling in R with the same interface. We specify the data, in which, in this case, I've defined the penguins data to be DF. And then we can write the formula without having to index columns of the data set by just naming the columns. So in this case, we want our response. We've labeled our response and our predictor. Oh, sorry, this isn't for the penguins data set. Sorry, this is just generally. We'd like to have our response, this tilde symbol, and then whatever the expression of our predictors is going to be on the right. In this case, we just, because it's simple linear regression, we just have the one predictor on this side. The stats model automatically adds an intercept. So that's something that doesn't happen down here. We need to be more careful, and this is what this row is doing for the array interface. As we define our model matrix X, which is something we'll go through that notation when we look at multiple linear regression, but we can use this this function from the stats model API to just add a constant, and this creates our essentially our matrix X, which we can then feed into the ordinary least squares function from this package. So as I said, we use a formula interface. We're keeping things as simple as possible. The formula that we use is just going to be body mass in grams G as our response, and then we want the single predictor to be flipper length in millimeters. This directly corresponds to this simple linear regression model formula, which is what we covered last lecture. Beta naught is intuitively going to be the intercept, so that's essentially what the predicted body mass is going to be for a flipper length of 0. Obviously, this isn't very a sensible prediction, so this isn't something we're going to be hugely interested in, but we'll still look at the results. And then beta 1 is describing the increase of the expected increase of body mass per unit change of the flipper length, so the slope of the model. All right. As always with linear regression, it's very simple. We use one line of code. We call the OLS function from the stats model package that we loaded. We specify our formula that we just noted on the previous slide, and then we specify that our data is going to be penguins. And we call the fit function to tell the package that we would like to fit this model using the data we provided, and we save that entire object in model. This is now a very kind of a more complicated Python object that has multiple different things that we can call. The first thing we want to call is the summary of the model. So once we've ran this code, we can then ask Python to tell us the summary of the model by calling model.summary. And this is our output. And this should be very, very familiar for people who have used statistical models before and coded statistical models either in R or Python. They always look very similar. But if you're not used to reading them, they can be quite complicated and overwhelming and difficult to spot what's important. And so the aim of the next few slides is to break down the information in this summary as kind of carefully as we can. So let's begin. The top block of the summary represents or describes to us the model level information. So to quickly summarize everything that's involved, we are it reminds us what the dependent variable is, so the response variable. It tells us the number of observations, which is our sample size. It describes R squared, which we just computed a few slides ago in terms of this Pearson's correlation squared. In this case, it's the same. Once we cover multiple linear regression, we'll talk more about the requirement for the adjusted R squared. So the adjusted R squared is a measure of the descriptive power of our model, but then penalized for the number of predictors. So to quickly summarize the motivation of why we need the adjusted R squared is that if you increase the number of predictors and the number of parameters of a model, you are always going to increase R squared. However, you typically in statistical modeling and in data science in general, when you're applying models, you're always interested in this trade-off between parsimony, parsimony. I always get those two mixed up. But essentially, this trade-off between making the model too complicated and overfitting the data. So this is something you'll discuss much more in kind of like formal machine learning courses. But you essentially, when you're training a model, you can always improve the fit to no end by just increasing the number of parameters, increasing the model complexity. But that's not always what you'd like. You typically are assuming there's some kind of noise, and it's completely pointless to make the model precise enough to perfectly model or perfectly describe noise in the data. And so this idea of penalizing models getting too complicated is balancing this trade-off between we want to try and maximize the information that the model can convey to us in as little, with using as little parameters specified, like without having to specify many different parameters. So it tries to find this balance. And so the adjusted R squared is this measure of as like a balanced performance measure. The S statistic is just the test statistics for the hypothesis test that the slopes, in this case, the singular slope, but for multiple linear regression, this would be for all the different slopes, or all the different parameters that aren't the intercept, testing the null hypothesis that these are all zero against the alternate hypothesis that they're all not zero. So in simple linear regression, this is just equivalent to a t-test because we just have the one parameter, so we just care about that parameter's sampling distribution. And we talked a little bit at the end of last lecture about how we can, for large n, assume this is normal, but for small n, we rely on the t-value. So that we don't have to we don't have to perform the inference ourselves. The output also provides the p-value for the F statistic in prob F statistic. And so we can always look at the p-value for this test and see whether or not at typically the 1 or the 5% level, there is significant, the model provides significant evidence that the slopes are non-zero. So we're always looking to see whether or not this F statistic is significant. So whether the p-value is less than whatever significance level we want, as confirmation that our model was successful and it is describing information. It also provides some information criterion. This is something, again, we'll discuss more when we look at more complicated models, but I again always get this pronounced wrong, but I think the Akane's information criterion and the Bayesian information criterion are both just, again, performance measures, which balance model complexity against fit and prediction power. And lower is better, including negatives. So we typically read these, we use these as model comparison tools. So on their own, they don't tell us any information, but if we were to fit multiple models, we can then compare the information criterion for multiple different models and see which one performed best based on this criterion. And then finally, another performance test is the log likelihood at the MLE. So this is just a third kind of performance measure to compare models against. So just to kind of highlight that, it's all going to be up here in this model. So this is all the performance measures of the model from R squared, adjusted R squared, F statistic. Having a look at this output for our model, we can see that the adjusted R squares ties on to what we looked at. The R squared ties into what we computed earlier as this 0.759. So it explains about 76% of the variance, which is very good. The F statistic doesn't give us any information on its own, but the p-value of the F statistic is very close to zero, essentially zero. And so this is incredibly strong evidence that the slope parameter here is non-zero for the data. And then, like I said, we can't really interpret these three unless we use them as comparisons against other models. So that's something we'll look at when we introduce multivariate linear regression. So this is just some code to pull out those values. If you ever need to pull information from the summary statistics, from the data summary, you can use this code, and you can go through this code line by line if you'd like to understand what's happening. We essentially pull the coefficient table from the model summary, and printing it. And here you can see we're pulling the intercept from the model parameters, and we're pulling the slope from the model parameters, and we're pulling the confidence interval. So I need to use my animations that I spent time making sure they work. Everything in the print functions is most certainly AI generated. I used it to make the output readable in terms of using mathematical notation. You don't need to worry too much about all this complexity. You can typically just print CI and see the output that you care about. But this is just to make it more readable in the slides in this nice format. Okay, so this is the most important section. This is what's describing, in this section, it describes our fitted parameters. You can see, first of all, in the first column, we have an estimate of the intercept, which as I mentioned before, is of no interest to us because we don't care about the case where penguins have flippers of 0 length. It's not reasonable to think about that. And you can see that our coefficient for flipper length, so this is beta 1, the slope, is predicted to be nearly 50, so 49.68. Those are the values of the parameters. And so from the slope, you can determine this is the, as flipper length increases by 1 millimeter, you can expect the was it weight or mass? Or I think it was the mass, but the mass of the penguin to increase by 1 unit. Let me double check. Body mass, yeah, by gram. Here we can just use the confidence interval function to pull out the confidence intervals specified in the model, which is always helpful. So this is the output. You can see that we have our standard error for the coefficients. It's usually quite helpful to see how the size of the standard error compares to the coefficient itself. If it's significant, if it's in roughly the same order of magnitude, you can have significant problems. But in this case, you can see that the standard error is significantly smaller in both cases. We performing our test to see the significance of these parameters. The t-test, we get the two test statistics here, and then this is our p-value for this test. So both p-values are so close to 0 that they've just been written as 0, which means they're very highly significant. And so none of these parameters are being superfluous for needs. If you ever have a high p-value, which is above your significance level, you'd conclude that that parameter isn't making a significant change to the model, and therefore it would be the first one that you discard if you're looking to simplify your model. And then here you can see the confidence intervals for the two parameters, which our prediction should lie right in the middle of them. Okay. So I just went through this. This is just a summary if you're ever reviewing the slides of standard error, the test statistics involved, etc. So hopefully that's self-explanatory. I think I've just discussed this. So the expected body mass when flipper length is 0 millimeters isn't very is nonsensical. We don't need to think about it. It's not very meaningful. The slope just means that we increase the penguin's body mass increases by about 50 grams on average per millimeter of flipper length. And both the p-values are effectively 0, so strong evidence that flipper length linearly predicts body mass. Finally, in the bottom plot, we see a combination of some more complicated metrics. This again is, excuse me, I'll have a sip of tea, which is really cold. It's okay though. I'm British, I'll still drink cold tea. Don't understand this iced tea nonsense that Americans love. However, they are tasty and sweet. So, excuse me, sorry. In terms of reading these summary statistics, so the bottom block includes lots of descriptions of the residuals, which we'll go through in more detail in a second. The idea of the residual analysis is that there are some specific things we're looking for. We're looking for the normality of the residuals, because that was one of our model assumptions. So that's what a lot of these metrics are looking at. We're looking at the omnibus and the probability of omnibus, which is this measure of the normality of the residuals. This is combined of the skewness and the kurtosis test. sorry, it's this a test for both skewness and kurtosis to see if they're similar to a normal distribution. We also the output also provides the skewness and the kurtosis. So remember, the skewness and kurtosis of a normal distribution are 0. This means the distribution is symmetric, and 3, which means its tails are similar to that of a normal distribution. So we're looking for these values to be close to 0 and 3. We have the JB, the Jacques-Berat test, and the outputted p-value for that test. This is again just testing the null hypothesis that the data is normal or vice versa. It's just testing for normality. And Durbin-Watson is a test for serial correlation. Ideally, this should be 2. However, I'm not. I'll double check this. I copied this from some notes, but I'll double check. This is typically something you care much more about in time series analysis, because your interest in serial correlation and like autocorrelation is this idea that there's some predictive power from the lagged values of a time series. But in this case, we aren't considering a time series, so we don't care about this output so much, which is why I don't think I should put ideal as 2, because I think this is ideal for time series data. And then condition number flags potential multi-collinearity, and this is something that's going to be more relevant with machine learning, not machine learning, with multiple linear regression. So these statistics give us an initial indication of fit. The whole point of them is to, at a glance, give you as much information as you can about the fit of our model, but it's always important to visually inspect the fit of our model through diagnostic plots. So diagnostic plots involves computing residuals and producing plots of them. So this is, again, just some code producing all of those statistics from pulling them from the model. So this is all. I've basically just included this code in case you ever need to make like automatic outputs of, instead of having to retype values, you can pull specific values from the model output. So then if you ever change your model or you'll change your data, it can update the values in your notebook for you. I'm not sure this is something that Jupyter can do, but it's definitely something that Quarto can do, which can be very helpful if you're making a formal article in LaTeX or something like that. But I digress. This part's not so important, but you can refer back to it if you ever need to pull those values. We'll move on to what is probably the most important part of the procedure for fitting the model. Once we've fitted it and we've looked at the summary, we visualize the fit. And so we can plot our regression line. And this is where I want to be more careful. So I'll break down what this code is doing. Essentially, to produce the regression line, we would like to generate the value of x's that lie in the range of values of our predictor variable. So this is what this is doing. If I kind of jump into the data frame that I'm constructing, because that's just a wrapper, I'm using this linspace function, which I set the minimum value as the smallest flipper length that we have in our data set, the maximum value as the maximum flipper length that we have in our data set. And I use linspace to generate 200 values between these two values at equally spaced intervals, so that there are 2 of them. I then just plug all of that into a pandas data frame so that we can reference flipper length in the same way as we would if it was in the data. The next thing is to feed this data. So this is all just possible values of our predictor. And so we can, in order to get the prediction, we just feed this into our fitted model with beta 0 hat and beta 1 hat. We can use that by calling this model object, which we saved from our initial regression, and calling the get prediction function. We plug into the get prediction function our grid of values, and this get summary frame is just a way of returning the specific values we want with the significance we want. So this is pulling the confidence interval values as well as the predictions. If we were to ignore this, we would just get the predictions. But if you ever want to return the predictions along with their confidence intervals and their prediction intervals, you can return this summary frame specifying your significance level. So in this case, we want a 95% confidence or a 5% significance level. We then just proceed to produce a plot. So the first step is just scattering the points. So I apologize, I should have had some comments breaking these down. we produce our points here. So this is exactly the same scatter plot that we produced in our exploratory data analysis. However, this one's not using Seaborn, just so I can stack all the different layers that I want. But we just use ax or the scatter plot from matplotlib, calling our values and specifying all of our different formatting features on the bottom. In axplot, we're producing the best fit line here. So here you can see I'm specifying the x values to be this gridded values of x values that I defined in the first few lines of code. And then the second one is this prediction that we've produced. So I'm pulling out the mean. And this is something that I recommend if you run this code, you have a look at what this data frame pred_ci that we pulled from model get prediction 2 lines above, what it looks like, because it will just have multiple columns of the mean and then also the mean confidence interval and prediction confidence intervals that we can pull out. So you can see that in this next line of code, I've used a matplotlib function called fill between, in which we essentially have to specify 2 lines of points, and it will connect all those points as lines and fill the region in between them with some kind of color. Everything on the bottom is just formatting options, but you can see here, I specify the x values, I specify the lower line for this region, and then the upper line. And this is pulled from, again, from pred_ci, but specified the mean confidence interval lower and the mean confidence interval upper. Okay, and then everything else is just plot formatting. But it's important to stress that this is the mean confidence interval. This isn't the prediction confidence interval. So this is going to be a tight bound around the best fit line, which is telling us this the confidence interval for the mean of if we were to make lots of predictions at that for that response, this is where they would all group around. Okay, this is the result. So as I said, the confidence interval for the mean is this narrow band appearing around the best fit line. And as I mentioned, this is essentially just saying if we pick this level of our predictor, and we did lots and lots of sampling for, well, we sampled up to the number that we've sampled here for n. This is how close the mean of that collection of samples would appear at that point. So this is our first time looking at it though, so it's worth having a look, having an inspection of the data, seeing how well it fits the data. And this seems very reasonable, right? Like it seems to have be passing very evenly through the cloud. The mean confidence interval is Boeing's, or has sort of a dicky bow, and we say in England, I don't think you say it in America, but like this bow tie shape where it's tighter in the middle and a bit looser towards the outside. That's typically because more data is focused in the center of a cluster, and so you can have more confidence about the mean in that case. However, in this case, it's sort of the effect has been suppressed somewhat because we actually have a focus of the data in 2 different points, and so we have a bit of sparsity of data in the center. But I digress. We can also add the prediction level. So this is exactly the same code as on the previous slide. However, we're adding this second fill between, this time calling the observed confidence interval lower and the observed confidence interval upper rather than the mean confidence interval. And we just produce the same thing. We just change the color from crimson to steel blue. And you can see that we then have this prediction interval, which is this much wider interval. So the prediction interval captures 95% of the predictions. So you can see here that in this case, it's doing a very good job. By design, it's captured this nice kind of majority of the points. And it can also help you to identify these outliers as well. So you can see here, around both of these clusters, there's a couple of values which potentially had the risk of being very of distorting our best fit line. However, they're not too, they're not too extreme in this case, but you can imagine what would happen if we had a point down here and how much it would be pulling down this best fit line, even if it's just a singular point in this data cloud. And so this can be a helpful visualization to see what the most extreme values are under this assumption of a linear regression model. So in terms of making specific predictions, I talked about this a little bit last lecture. your model is essentially, once you've fitted your model now, you have a deterministic part and a noise part. So every single time you have a new observation of flipper length and you would like to model the body weight in grams of a new penguin, every time you plug in that predictor, you'll get the same response up to adding the noise. So it's just a linear model. You will have beta naught plus beta 1 times by whatever the flipper length is, and that is going to be your starting point, essentially the center point, and to which you can then add noise using the sampling variance that you estimated for the error of the noise. So all this code is doing is using the model to predict a new penguin, I use new penguin for the data, so it's predicting the body mass of some new penguin we've added to the data set, which has flipper length of 195. And we're asking it to tell us what the new body weight is going to be. The predicted mass is 3,907 grams, so we can have a look at this in our data set. And specifically, we're pulling out the 95% confidence interval for the mean and the 95% prediction interval. I think I add this to the plot. Oh, no, I don't. But we can have a look at this on the plot anyway. So this has got 195. If I just skip back here, 195 is roughly in the center here. So this is where this 3,900 is coming from. It's just literally pulling out this value here. And if we wanted to simulate this population from our model, we could obviously just add the noise back. But this is our best guess for what it's going to be based on our model. Because remember, the prediction is going to be the expected value of y. It's the conditional expectation of y given x. So our predictor, we're plugging in our predictor and it's giving us out the expected value of the response for that predictor, which is going to be centered directly on our line. I keep wanting to say any questions, but that would be pointless because this is a recording. Okay, on to some residual diagnostics. So the whole point of residual diagnostics is to check the assumptions. So when we first discussed, in last lecture, when we discussed the theoretical properties of simple linear regression and deriving these estimates using ordinary least squares, the parameters being unbiased, using t-inference, assuming all of that analysis that we performed was built upon this assumption of the Gauss-Markov conditions. And one of the easiest ways to incorrectly fit models is to fit them to data that don't satisfy those assumptions very well. If those assumptions are violated, our estimates may be biased. These properties might not hold anymore. The standard errors might not be correct, and the p-values might be misleading. So even if the original summary output of the model looks reasonable, it may still be flawed if these assumptions are not met. And typically we have a look to see whether or not the assumptions were met by examining the model residuals. And that's something you'll have a bit of practice on in lab 1 of this week, lab 1 of next week, where you will fit, you'll have an example of simple linear regression using the student performance data that you've looked at in lab already, which has a very strong linear relationship and everything works brilliantly. And you'll have a second example of some synthetic data which have this polynomial curve, which violates this one of these underlying assumptions, and you'll see this violation make both your model summary output problematic, but then also your residual analysis. You'll be able to see it clearly through the residual analysis. So we can never verify these assumptions perfectly. We can never confirm these assumptions perfectly, but residual plots give us the best available evidence we can. The four plots we'll be considering are the plot of the residuals versus the fitted values. This checks for linearity and homoscedasticity. We'll have a look at why that is. We'll look at something called a QQ plot for the normal distribution. So that stands for a quantile-quantile plot. Some of you may have seen it before, but if you haven't, the quantile-quantile plot is essentially, we have quantiles from a normal distribution on one column, and then quantiles from the empirical distribution of the errors on the other plot. And if they both lie, if the errors are normal, then all of the points on the QQ plot should lie on a perfect diagonal. However, if the data is skewed or has heavy tails, you will see the tails of the normal of the QQ plot either curling down into S shapes, curling up, or bowing one way or the other. So by looking at the tails of a QQ plot, if it doesn't lie on this nice straight line, you can assume that there is some lack of normality in the tail of the residuals, which means it wouldn't satisfy the fourth Gauss-Markov condition. We look at the scale location plot. So this is again looking for homoscedasticity. This lack of constants. Is that the right word? Maybe this lack of the variance being constant across all of the different observations. And then finally, we'll look at something called Cook's distance. So Cook's distance is a way of determining which of the observations are the most influential to our fit. And this can be a very helpful plot for refitting models and removing some outliers to the data. It can be an additional confirmation that you need to remove specific values because they seem unreasonable. So the first plot, I think this produces one after the other, right? Okay, yeah. So sorry, this weekend's been a blur of document creation and preparation, so I'm getting a bit mixed up in my head between the labs and the lecture. So to produce the residuals versus fitted, as always, we pull them from our model object. We pull the fitted values with fitted values and the residuals with resid. And then we just produce a scatter plot. So this is all very, very familiar stuff from when we looked at matplotlib. The only thing that's new here, which is something we're going to cover in a bit more detail when we look at non-parametric models, so kind of Lowe's regression and other things. But this is essentially just, whoops, what did I just do? What did I just do? Oh, I went outside of full screen mode. Sorry, let me just quickly move back to the right page. I got too excited. This is just a way of fitting a non-linear best fit line. It just essentially just draws the a non-straight line that best passes through the cloud of the residuals. So this is more just for visualization purposes. You could also just produce the same thing in Seaborn. In fact, I may change the slide so that they do, so that it's more familiar. But everything else is just additional formatting things. So this is adding a horizontal line, et cetera, and this is all just formatting conditions. So this is what the plot looks like. So the low as smoother. This is just this sufficiently smooth line through the data. So this can be thought of as like a best fit line, and this is just highlighting where 0 appears on the y-axis. So ideally, for the residuals, we would like to see random scatter around 0. We don't want to see the residuals showing evidence of any sort of patterns or trends or kind of oscillations in any way. Banding, for example. Here again, as we've discussed, you can kind of see these kind of two clusters appearing. Sorry, I didn't mean to push that button. So this is, some evidence of this kind of hidden variable that we've not considered yet coming through. But overall, this is a reasonably good performance by the residuals. We can see that the low smoother, as much as it's curving and bending, it's hovering around 0. It doesn't, and it's not showing any sort of clear trend one way or the other. So as I said, we're looking for points scattered randomly around. I keep doing this. I keep kind of jumping ahead or talking about a plot and then not moving ahead. Looking at points scattered randomly around the horizontal line at 0. We don't want significant curvature. Like some wobbles and oscillations are okay, but we don't want a very clear curve coming through. We want a constant vertical spread, so we don't want the residuals to be tight further down and then get further much wider later on. And so it's kind of summarizing some of the warning patterns we can look at for this plot. We can look at if there's a curve, then the likely violation is for linearity, and we could try adding polynomial terms. If we have kind of this fanning or funneling shape, this bugling shape, as I've been calling it, we could look at different kinds of modeling, or we could try transforming the response variable. This is a very common property you see in financial data. So if you're ever trying to fit linear regression to financial time series data, which sometimes you'd like to, like kind of time series linear regression, you typically will take the log transform of y to decrease this heteroscedasticity that you always see in it. And then stripe bands, which is this kind of possible discrete admitted variable. And so you'd add some kind of grouping variable, an indicator that tells you where which group the data is from. As I mentioned, you can see a kind of some mild vertical banding. So this is this hint that we have this hidden species variable. We'll look at adding species as a predictor when we consider multivariate regression later on. Although I promise we won't just consider the penguins data set. It's just so nice to work with. Checking for the normality. So this is pulling from, again, the SciPy stats. You can construct these manually, but it's too much of a pain. We just import probplot and we plug in to the function probplot the residuals, and we specify we want the distribution to be normal. And then from that, we can use the scatter function and just calling the first. Well, it's because it's stored as a list of values, but we take the first element in the list and then the first data frame from that list and then the second data frame from that list to get our quantiles for the normal distribution, or sorry, quantiles for the data and then quantiles for the normal distribution, and produce the resulting plot. So this is what things look like. You can see we have this diagonal line, and you can see that in this case, the points lie very, very close to this diagonal line. So this is a strong indicator that the points are Gaussian. You'll typically always see some kind of decaying away from the distribution at the very, very end of the tails. This is, not often it's, you learn what a significant change looks like, but in this case, it's very, very negligible. It's hovering very close to the normal distribution. So as I said, done it again. As I said, points in the line is good. Heavy tails or an S-curve is evidence of leptokurtic data. So it has more extreme values happen more often than in the normal distribution. If they have light tails, you have this platykurtic, so fewer extreme values than normal. That's the curve, instead of going into the shape of an S, is going the opposite directions. And then any kind of systematic curve is you have some skewed residuals. So you typically need a transformation. So this is just a very quick breakdown of what you might consider if your residual quantile, your residual QQ plot displays any of these different properties. This is definitely something that we'll discuss a lot more when we consider different kinds of models, because you, as a data scientist, will spend a lot of time evaluating different models, comparing different models, and trying to make a decision about which one's best, rather than having a very clear mandate of knowing exactly what you want, exactly what model is appropriate, and the data being perfectly suited for it. These are obviously very nice examples, and typically your workflow as a data scientist is going to be first trying to determine which models are potential candidates, fitting multiple different models with multiple different parameter combinations, and then using your own judgment and intuition, as well as information criterion, to evaluate all of those different models and select which one you think fits the data the best before you then proceed to make your inference or your predictions. So that's kind of the broader workflow that we're hoping to work towards, and what I hope that you can apply in your final project. So why normality matters and when it doesn't. So normality is required for exact T inference in small samples. We've spoken about this before, and this is something that you should be very familiar with from 120. For n greater than or equal to 30, roughly, the central limit theorem means that t-tests are approximately valid regardless. A slight departure from normality in the sample. A slight departure from normality in a sample of our size isn't a serious concern. But evidence of extreme outliers and strong skew are always worth investigating. So the scale location plot is produced by pulling out, we've already defined the residuals in a previous code chunk, and then we take this residual standard deviation by applying the computation of the formula that we derived in the previous lecture. And we take the square root of the absolute value of the standard deviation, and we just produce this plot. So this is what this plot looks like. We have the standardized residuals here against the fitted values that we've computed. Again, we're looking at this, we're looking for constant variance. So we're looking for this line to be, well, I'll go on to the next slide because I remember that I now have these. Oh, I don't even have it for this one, which is how that's annoying. But we're looking for this nice smooth flat line once again, looking for constant variance throughout, and we can see that it is what we're getting in this case. So finally, Cook's distance, defined by this DI, measures how much the fitted values change if observation I is removed. So the way that this is computed is that we consider how much the fitted values of our model would change if we remove that observation. Obviously, for most of them, it should be very small. But if we have a particular outlier that's a very long way away from the line, it has a disproportionately large effect on the parameters if we remove it. That's something that we call influence. So if we have a large Cook's distance, we call the point influential. And this influence is coming from a couple of different things working together. So first of all, it's the residual being large and the point having a very high leverage. So it's both the error is very large and the and how unusual the observation is relative to other predictor values. We often kind of, particularly on plots, we produce this common threshold of roughly 4 over n. So most of our plots that we're producing by hand will also add a horizontal line at 4 over n, where n is the size of our sample, as our threshold. So you'll see the resulting plot as we typically use a H-line plot. So, or a stem, sorry, not a H-line plot, that's the horizontal line. We use the stem plot, which produces vertical lines for all the points we specify from 0. We compute the influence, or we obtain the influence from the model using getInfluence. We then compute Cook's distance by pulling the Cook's distance out of this object we've just pulled, and then we can compute our threshold for our horizontal line. You can see in here, we add it in the horizontal line here. And then for the stem, we just have the range of this, we produce a range of values. So this is just indexing over however long the Cook's d is, and then we plot all the Cook's d's as stems. This is just a line of code that's identifying the points of interest and giving them different formatting. So you can see here, this is what our Cook's distance plot looks like. And the idea is that you can just identify points that are above the red line to see what the highest, the most influential points are. So you can clearly see there are several in this data set, but the two to look out for are at index, roughly 40 and around 240 as well. You can obviously find these exactly by returning this data, sorting it in size and returning the index so that you can identify these points exactly and see which observations they correspond to. This is just some code that you can look at on your own. I'll try and make sure that I don't know if you can scroll them on the PDF, so I'll try and make sure that I potentially try and condense it, but I'll definitely make sure there's a copy on the lecture notes that produces this diagnostic panel. So it essentially uses matplotlib to create this multi-plot with 2 rows and 2 columns, and then produces all 4 of those plots we just discussed. I'm just checking the time quickly. We've got about 15 minutes left. And this is our result. So this is something I would actually recommend if people are interested in, kind of continuing with their data science journey after this course. This is a really good candidate to define your own function. So to potentially have a script in which you define your own functions, and you can essentially just have your input to the function be the model, and have this be automatically generate your residual plots. I'm sure one already exists in different packages, but it's good practice for starting to define your own custom functions so that you can apply things exactly the way you want to, and you can control your formatting exactly the way you want to. Just a side quest for this course if anybody's interested. This is all the plots we've just seen, obviously. So it's just a very quick summary of all the information we need. Overall, this is a very strong fit. As we mentioned, the data is very well suited for simple linear regression. And so we move on to a case of showing an example of when we have, oh, sorry, there goes my cat because my wife just walked in. Something called Anscombe's quartet, which is a very famous data set example showing cases where we have several different data sets who have very similar, or I think identical, parameters and statistics that we compute, but very different shapes. So they share the same summary statistics, but look completely different visually. So it's an example to highlight how important data visualization is. So if anyone wants to produce these on their own, you can use, again, from Seaborn, you can load the data sets from Seaborn. This is just automatically computing a selection of summary statistics and printing them all together to show you that they're all the same for the different data sets. Excuse me. Too much talking and too much tea. They all have the same sample mean for both the observation and the response. They all have the same R and all have the same R squared. So from our summary, it looks like each of these models describes 66, I mean, slightly different here, but 66 to 66, roughly 66% of the variance the observation describes, roughly 66% of the variance of the response. However, if we produce the line, so this is just a quick for loop. This is definitely something I used ChatGPT to help me produce because I kept making a mistake with this zip. So I appreciate its help producing this plot very quickly. But you can see the clear differences between the data types and the patterns they're showing, and why some of them are very well suited for linear regression, some of them are not, and some of them would be suitable for linear regression if we didn't introduce some very strange outliers. So I think I do an outrun of these. Yes. So I'll summarize them, but since we have it visually, looking at plot one, this seems to be a very reasonable data set to perform linear regression to. There's a data cloud with relatively constant variance, although there's not enough points ideally, but we can forget about that for the time being. And the cloud seems to be moving in a linear direction. Plot two is clearly not suitable for linear regression. We have this very, very obvious deterministic curve shape to the data. And so this could just be something that we actually could describe perfectly mathematically. I'm sure that's how it was constructed. But trying to fit this best straight line to what is obviously curved data is where our problems are coming from. For data set 3, we actually have a straight line of data that's been just added one extreme outlier, which has a very, very strong leverage and a very strong influence on our line, which has pulled our best fit line up off the line originally. So this could be a case where you would be interested in disregarding the single point to have linear regression be suitable again. And for the final data set, it just shows how how we can have this very, very strange distribution of points, but the best fit line can just, doesn't really convey information about the location of a majority of the points. Most of the points are just hovered around, centralized around 8 with different y values, and then there is just one strange outlier far away, which is where the lines draw into. So here, you can see the quick summary of those points. Number 1, linear relationship, random noise, simple integration is very appropriate, proceed normally. Curved nonlinear relationship, we could use a polynomial term or use a different model, or like I said, I presume that this is probably quite deterministic, and so we can probably just fit a mathematical description, some kind of closed form expression for this model. Linear relationship with one influential outlier, so this is a case where you'd investigate the outlier or consider some kind of robust regression, or just remove the outlier. And then similarly, you've got one extreme leverage point, which is driving everything in this line. And so the point is, again, it's to identify, we're only able to visualize, we're we're only able to identify this point once we've produced the visualizations, and then we can proceed accordingly. So we can either remove the point or still perform the regression, but discuss this point critically. So the key message is always plot your data, always plot the residuals. I'm hoping that once we're finished with this class, it's become very algorithmic for you. You always start with loading the data, preparing the data, exploring the data with lots of visualizations and summary statistics, proceeding to model, and then once you model, you produce your summary statistics for the model and your visualizations for the model, and then you proceed to make your conclusions or make your adjustments and try different models or compare different models. So that's kind of what the rest of this course is going to be based around. So as a quick summary, sorry, let me move my face out of the way. The complete workflow for simple linear regression, which will basically tie over to multiple linear regression, is we load and inspect, we do our exploratory data analysis, but specifically for linear regression. So we're looking for linearity, looking for this satisfaction of the assumptions for the linear regression model. We fit using whatever our chosen function is. We can use this smf.ols function. We need to make sure that we understand how to read the model summary. And then after that, it's just a collection of plotting the predictions for the model, the best fit line, the confidence intervals, the prediction intervals, and then performing residual diagnostics. And that is our workflow for these kinds of models. So this is just a quick summary of our results. We found that flipper length is a strong predictor for body mass. We got the estimated slope. We can't conclude causation. This is something we talked about in week 1. This is always just talking about relationships, but we're not trying to show that long flippers cause greater mass. They're both potentially driven by other variables like diet, age, species, etc. And we should also be careful not to be too strong with our conclusions. We don't assume that it's the only thing that the only factor in this relationship, and we potentially could improve our fit by adding different variables, and that's something we need to explore. Sorry, I nearly skipped over that. One really important part when it comes to considering linear regression is extrapolation. So theoretically, we are very much constrained within the data we have observations for, and it can be quite dangerous to try and extrapolate, even though it seems very natural with linear regression. It can be very dangerous to try and extrapolate this relationship to outside of the data range that we've been provided. Sometimes it's safe to do so, but sometimes it isn't, and it needs to be very carefully considered. Typically, as a good rule of thumb, the model is only reliable within the range of flipper lengths that we have. So if you suddenly had a penguin with a much longer flipper length than normal, it would be somewhat foolish to try and use our model to predict what the body mass of that penguin should be. So anyway, as discussed, we'll move on to multiple linear regression in lecture 11. But in conclusion, we've covered simple linear regression. Sorry, that was my cat. I'm wondering if she'll jump in the lecture before the end of the class. Maybe it's a nice Easter egg for anyone who's got to the end of class. So we've covered how to fit linear regression in Python. We've produced all our visualizations, and hopefully this lecture can act as a lot of example code that you can then apply to your labs. Feel free to find more optimal ways of doing things. I'm going to turn my screen. Oh, I'm not sure able to see her, but she's just over here going crazy. Are you going to focus? Hello. And she goes. She's just a blurry blob, but she's there, I promise. Let me unblur my background, actually. Oh. There she is. This is Jinx, everybody. My cat. She's a dangerous wild animal, and she's going to attack my hand now, I'm sure. Anyway, so we've determined, we fitted linear regression in Python. We did all of our plotting. We've done all of our diagnostics, and we've had a nice practice with this kind of simple form of statistical modeling. Hopefully, it's very intuitive and relatively straightforward to apply in Python. We're going to build on this in the next few weeks by adding introducing more complicated types of linear regression. So multiple linear regression, where we add different predictors, going through the formulation in linear algebraically, and how it impacts all of our different model diagnostics and the kind of the more complicated analysis that we have to do for model fitting. But yeah, I hope your labs go well, and if anybody has any questions, please drop me an email. But thank you very much. To end the recording. Okay, I'm gonna keep doing this. Where's my? There we go. Oh, the lag is pretty appalling.